So hi everyone. Today's a really nice lecture because we are going to prove Riemann's theorem, define what is a genus using Riemann's theorem, and see GOPA codes, and that's in the first hour. And then in the next 2 hours, we are going to start our way towards proving Riemann-Roch, which is again like a downfall in terms of what you get and what you have to invest. But let's start with the good news. So recall last time we proved the following theorem, which is actually a kind of a major theorem in the foundations of this field. And it says that if you take any element in function field but not a constant, then we know exactly what is the degree of the zero divisors, namely how many zeros this function has. It's the same as the number of poles this function has, which algebraically is precisely this expression. That's usually easy to understand, and so you immediately get like the number of zeros and poles. And in particular, of course, the degree of the principal divisor, which is just this minus that, is zero. Every function has the same number of zeros and poles. Good, and the proof wasn't easy and so forth. I think it was kind of weird. But in the midst of the proof, just recall, because I want to continue, like from the part of the proof that we did, we finished the proof, but I want to do something else using the proof and not the theorem itself. So recall that we proved something like this, so it was, right, so you need to kind of go back in time, but I'll try to remind you. No, that's actually is part of the proof, I'm copying the proof. Yeah, but that's still okay. Happy accident, I copied the right thing for the wrong reasons. Okay. So in the proof, we started with this x that you gave me, and then x determined the k, not really important how, there was an integrality stuff going on and so forth, but this thing is a function of x, just this k, and then L was chosen afterwards, and we eventually chose it to be large enough. But generally speaking, we prove this for every L. Okay, for every x, there is an k such that for every L this holds, and then we took L to infinity and got the result that we wanted. But that's what I want to use now. Yes?
Types of k and n are integers, and the dimension is
Right. Right, so these are two integers, and you look at this divisor, which is some multiple of the pole divisor of x. So essentially, you take x to this power as a function and look at the poles of that, because you can put it inside this k plus L. Right. And here, these are just like numbers. Thanks. Any other questions? Because I'm kind of diving into the proof. Okay. So just looking at this, you can immediately see something that's cool. So k was some number that we got in the proof. You started with an x, and we chose this k, if you remember, to be large enough to win all the yj's. There was some, I don't want to get into the details, but k was right right constant in that is independent of L. Right, good. So given x, there was some k that corresponds to this x. It was kind of magical, like it was weird. I mean, you don't really know how to compute it, but it was some number. It has to win all the poles of the yj's, that blah blah blah. But then the point is that afterwards we chose L, and that holds for every L. And by choosing L large enough, we kind of got over the fact that we don't really understand k, but just a constant and so forth. Okay. So as a corollary of that, let's prove something that's most of Riemann. So for every function that's not constant, there exists some q. It depends on x. So let me just denote it like q sub x here in the notes. It doesn't appear like that, but let me denote it like that. I think it's better. I'll change the notes. So there is an integer for every field element, for every function. There is an integer such that for every m in n, if you look at the degree, what we call efficiency, degree minus dimension. Right, so there is some constant depending only on x. So once you fix x, it's fixed, such that for every m, if you take this divisor, right, which grows with m, essentially taking x to the m, that's what's happening here. And look at the degree minus dimension, the efficiency of this divisor, it's bounded regardless of the value of m. Okay? And that's actually meaningful. I mean, we know by the monotonicity property that if you take a divisor and increase it, the efficiency can only increase. Right? It was some theorem that we had, deg b minus dim b increases as you increase b. And this is the b in our case, and you do increase it, and it does increase and increase and increase. But this corollary tells you that it doesn't increase so much. So for every x, there is a bound for how much it can increase. It can go like, it's not a function of m. Every element has a bound for how much these, taking its powers, looking at x to them, how much the efficiency changes.
But it doesn't depend on x.
It does depend on x, yes, but it is independent of m.
Like, the definition of f over k of x depends on x. So it's the same, right?
Yes, right. So q of x is going to come from those things. Yeah. So right. So you'll see in a second that q of x is a function of this k also, and also of these numbers. But I mean that k I think depends on those numbers implicitly. But yeah, right. So yeah. So it can depend on x, but not on m. That's what I'm saying.
So how do you know that? Like, take different values.
I don't know.
Not the-
How it depends on x. No, I don't know. Right. So if you look at the proof, I mean, there was so you work with this yj. There was some integrality argument, and there was this yj's and the y. I don't know much about the yj's. I needed to win the poles of the yj's. You can't go. Okay, you shouldn't think of it. Right. You should just take it like that. And I agree that it's kind of annoying that, you know, it may not seem like much. You take one element and you say, well, the efficiency of x to them. This is just the degree of x to them, right? Also dimension is them. So you look at it and you say, well, you know, it's nice, but x to them is just, you know, for every x you have another bound, right? But that's still, you know, non-trivial, right? And so, but it's obvious from here. So you just like, you just need to call k plus lm. So let's just call m k plus l. That's what I said here, and just copy it and see that we're essentially done. So right. So what this tells you? It tells you. So this is m, and this is like m minus k plus 1. Right, L is m minus k. So from here, you get the dimension of the Riemann-Roch space is at least m minus k plus 1 times the degree of this pole divisor. I just stare at it for a second. It's fine. I mean, this is m. So this is the dimension of m times x infinity, like that. And L plus 1, just m minus k plus 1. I just copied it. And OK. Or, you know, if you want to say it differently, so with that, you know that for all m, so this was, right. So equivalently, if I'll take the degree to this side, minus dimension, because I want to look at the degree minus dimension. Right, so here I have the dimension. The degree, you know, m can go in and out. In dimension, it cannot. So I'm taking this m, putting it inside the degree. So you get this here. I'm taking this to the other side and keeping this here. And this is bounded by this k plus 1 that I have left here, k minus 1.
But it was getting something for all.
Right. So there it was for every L. And I'm just using that by taking, calling my m k plus L. Right. So this means that m is at least k. This holds for every L larger or equal 0. and this holds for every m larger or equal than k. Yeah, don't worry. Yeah. It will. Right, so maybe I should say it. Like, for every m larger or equal than L, as you said. So far I'm using that, I'm only worrying about all the m's that are larger or equal than L. You get this thing, right? I'm just moving around. I move this one here. But there is the degree. Here. Sorry. Yes. Larger than k. Yeah. Right, and this is independent of m, right? Because x is independent of m and k was a function of x, which is independent of m. So this is the bound that we wanted, except as you said, for the fact that we haven't considered the small m's. But we don't care about the small m's. Why? Because it's monotone. You can do that. You can say, well, there are only finitely many things. I can take the max. But you can also know that it's monotone. Like degree minus dimension is monotone. So if you bound the degree minus dimension for large m's, you bound it for small m's also. Right? But you can do both. Okay, good. So at least we know it's like a chain, right? You took an x, you picked an x, and then you increased it. Looked at x to the m's for larger and larger m's, and you saw that the deficiency doesn't change. There is some bound to it. It changes, but not infinitely. There is a bound on it. And remarkably, and now it's like if there was like a tada, that's essentially almost like you need two tricks to get Riemann's theorem from this. So, and again, Riemann didn't prove it, right? He proved it for complex valued function, and I think it was like Schmidt or someone, I'm not sure exactly who, that proved all of that, and it doesn't get any, maybe Dedekind and Weber, I'm not sure exactly who, they actually proved it for this general setting, but it's still called Riemann's theorem, even though the proof is completely different, right? But let me say what it is. So let's say you have a function field, and you take an element x that's a proper function, not a constant, and define q sub x as the maximum of the degree of mx, infinity, minus the dimension. Right, why can I say maximum? Over m? Right, that's what you just proved. You can do that. There is a maximum to it. And then what I'm saying, so you took an x, you figure out what's the largest value possible in the deficiency of these things. But what I'm claiming is that this bound holds for all divisors. So for every divisor, it doesn't have to be like a principal divisor. It can have nothing to do with x. It can have degrees that are much larger than those of x, whatever. The degree minus dimension of A is also bounded by the same number. So that's the worst case, really. Any divisor. Yeah. So that seems like a easy case, but actually that's the worst case. Right, in a sense. Yes. No, it's finite. Right, in the previous theorem, we said that for any given x, there is a bound depending only on x. Right. Only on x, mx is just x. Only on x, right, from here you know that there is a bound that depends only on x. It's defined, well defined. Yeah, right, so from here it will follow immediately that q of x is q of y, because it holds for every divisor, right? So you can pick an x and use this theorem with a which is y, like y infinity, and you'll get, or my infinity for larger m's, and you'll get the bound, but you could have started with a y and used the bound for x. So right, so from here, it's a corollary afterwards, but maybe just for fun, we'll say that. See, something happens here. It's not clear. So let's prove this, but you know, that's fantastic. It means that there is a number. I mean, you initially chose it using some function, but there is a number which is an invariant of the function field. It has nothing to do with these x's that you chose that kind of bounds the deficiency. And that number is the genus, or the genus minus 1, you'll see in a second, but it's the genus. Okay, so, but let's start by proving this first. Right, I mean, once large enough, yeah, high enough. Once you go past all the irregularities, really. once you go high enough to encode all the algebraic relations, something like that happens. Yeah.
Before, it doesn't really depend on it.
Right. It doesn't, right? It answers your question, but at least at the time that still at this point of time, it does depend on X. We have to prove it. Yeah, but the proof is a bit like I don't know, PG, like that. So, right. So first of all, you know that the deficiency, which is degree minus dimension, is monotone. I want to prove it for every A. So the degree minus dimension is monotone. So I can assume that A is at least the zero divisor, because I can otherwise just prove it for the maximum of A and the zero divisor. Right, so we can assume, I can increase A as much as I want. I was given A, but I increase it, prove it for that, and then I'll infer it for the original divisor. We can assume that A is at least zero, the given A. Okay, so now I'm going to do something a bit weird, like two flip-flops like that. Which it's hard for me to explain the rationale for them. Partially I can, but so I wrote this like that. Okay, I'm doing this because on one side now I have something which has nothing to do with A. No, it's just look at it. It's just, this cancels out, and this is the same as that. Right? Yeah, you kind of expect something deep, but it's just the same number, the same divisor, sorry, and just A is larger or equal to 0, so minus A. Because of the monotonicity. Right, you know that if A is smaller or equal than B, then deg A minus dim A, the deficiency of A is at most the degree. Right, so if you're given A, you can take as B the maximum of A and B, of 0 and A, and then so you can assume that your A is, so yes. Good, so you do that because now I'm going to use the monotonicity, and here you have no A. So we know from here that the degree minus dimension of that is at most the degree minus dimension of this. So we know that the degree minus, so this is the divisor that I'm looking at here. The degree minus dimension of that divisor is at most QX, right? The degree minus dimension of this thing. And why am I doing that? Because I want to kind of be assured that there is an element in this Riemann-Roch space. So I'm looking at this dimension. I'm going to take it to the other side. I want it to be positive. So I'm taking it to the other side. So from here it follows that this expression, okay, is at least this thing minus Q of X. Right? This thing, M can go outside in degrees. So it's M times the degree of X infinity. And then you have minus the degree of A, limited minus Q of X. Right?
So when you say less or equal, you mean there is at least one.
These are numbers. Here?
Yes.
Right. So
There's one, like everything is like equal. In the worst case, everything is equal and one is only equal.
if it is strict, if it's right. When it's like that, for every prime divisor, the VP of that is at most the VP of that. Good, so you have this, and now, right, these are just fixed number independent of M, and this is non-zero. Like, right, X was chosen as a function, not a constant, so it has a pole, and because it has a pole, this has degree at least 1. Everything here is positive, like the negatives of the pole, so everything is positive. So this is at least 1, and so you can take M large enough so to make this larger than 0. For large enough M. Right? You use the fact, kind of a non-trivial fact, that every function has a pole. But other than that, it's obvious. Good. So let's take an element there. So, so there is a y in the Riemann-Roch space, a non-zero y in this Riemann-Roch space, whose dimension we just proved is at least 1. Right, there's someone there. You can make many things happen there. But there is someone there for some m. Good. So another way of writing it is saying that the principal divisor of y plus m times x infinity minus a as divisors, it's at least the zero divisor. Right? Because this is generally speaking when is an element in the Riemann-Roch space. Its principal divisor plus this divisor is at least the zero divisor. But let me massage it a little bit. You can write it like that. I just move things around, and I took this y to the other side. So the principal divisor, so the minus of the principal divisor is the principal divisor of y inverse, right? Because you change the poles and the zeros when you do minuses. And now again, I got this. I told you there's a flip-flop. So now again, I got this same situation where there is something that depends on A and something that doesn't depend on A. So something depends on A, like here we are with more knowledge about it, but something that's depends on A, but not on M in this case, actually, and something that is independent of A. So again, by monotonicity, we know that the degree of this divisor minus its dimension is bounded by what? Qx, exactly. But I claim that we are done. I'm claiming that we already know that this is deg A and that this is dim A. Right? You just have to remember that. So that for the degree, it follows, because we said that, but let me repeat. The degree of a sum is just the sum of the degrees. So you have the degree of A, and then you have the degree of some principal divisor, which is 0. Right? Every function has the same number of zeros and poles. So that's the degree. And another way of saying that, that's how we said it last time, is that the degree doesn't depend on the divisor, but on the divisor class. If you add the principal divisor to it, the degree doesn't change. And same for dimension, even though it's less, actually it's easier, but this required us to prove something about the degree of principal divisors. Here, there was just an isomorphism between this Riemann-Roch space, L of that and L of A, just by multiplying by y. Y inverse, I'm not sure. So it's just an isomorphism, so these are two vector spaces of the same dimension. And we're done. That's what we wanted. Yeah. That's cool, right? I don't know. Yeah. Yes. I agree. But when you see the proper proofs, when we're doing like curves, you also do the same tricks. You take a function, so I mean, I don't know of another proof. Like usually you work there with functions, sometimes not. And then you take them to a power, which is exactly doing mx, and you do that so to make sure that there are maybe some intersections that you can't handle. These are like the small k and stuff like that. But above that, you can say something. So all the proofs are. It's kind of I think for mathematician, this is the analog of padding argument. Like once we do padding, like add zeros, like it's like, okay, just don't worry about the easiest. So that's that. And you see it in other contexts as well, by the way, not just here. But that's the thing. Let me keep Riemann's theorem for a second and not erase it, and erase the proof. And that allows us to define the genus of a function field, which is remarkable. Like we did it completely algebraically. There is no geometry, no topology, like no complex analysis stuff going on. It's completely like abstract, which is good and bad, right? I mean, it's good because now you can do geometry over F5 something, and it's bad because you don't understand what happened. So, but no one like what is understanding, right? So this proof will remain the same even if you knew how to prove it geometrically. So the only thing that you will feel is you'll feel better. You feel like, oh, I know what happened there, and I can spot some relations, but analogs. But like that's where I'm sitting. So is that implied that I understand this? No, it actually, I don't know. Yeah. What is understanding? Okay. So But at least with this theorem, we can finally define the genus. So let over K be a function field. So the number G satisfying. So technically you should take G minus 1, you'll see why. I mean, it's just a choice, but it's a better choice. So right, we said that the degree minus dimension of every divisor is bounded. So the genus is essentially the maximum or the maximum plus 1.
G minus 1 of G to the minus. Okay.
Right, yeah. This is called the genus of the function field. Right. So now if you know complex analysis, you have this notion of a genus which has something to do with all of these loops going around and how many holes you have in some surface. And that generalizes that. That agrees with the genus from complex analysis or Riemann surfaces. But that's like, you don't need those things. It's all algebraic. Algebraic is like more basic, right? I don't know how to explain it. Like there is addition and multiplication. There's nothing there. Division. Only two groups acting around. There is no geometry. You don't need geometry.
Maximum number of imbalances you can is if you have a 0 in every pole, like that's the idea.
Yeah. And actually, yeah, we'll talk about differentials. If you know these things, you can maybe spot some relations. But at least for now. Yeah. So that's the genus. That's the definition. It's an important definition. It will be an important parameter for our codes. So we like this parameter. And just as a remark, and that's why we define it like to be G minus 1 and not G, or I don't know, maybe just to be like to have like a backward compatibility with the previous definition. But it's a good definition because note that G is at least always at least 0. I mean, it can be larger. It was one of your exercises. Oh, I'm not sure. Yeah. Actually, I'm not completely sure that we proved it. Only maybe for A, which is larger than 0. So we said something about the dimension can only be the degree plus 1. So this is always non-negative. But I'm not sure we actually proved it. I'm not completely sure. We'll see. But what I'm saying is that that's what I'm saying now, right? So it's always non-negative. Sorry, that's what I'm doing right here. Okay, so it's always non-negative. I thought of something else. So, and the reason is because you choose the max. Now I understand what I wanted. Forget about it. The reason there is a max here, I mean, because there is a max here, one of the competitives for the maximum is the 0 divisor. And for the 0 divisor, so G minus 1 is at least if you take this with the 0 divisor, and the 0 divisor has degree 0 and dimension 1. Because K is there, like the Riemann Roch space of the 0 divisor is K. So this is 0 and this is 1. So right, G minus 1 is at least minus 1, so G is at least 0. This is like 1, not with the minus. Good. And maybe another good reason for defining the genus like that, rather than with the other, not minus 1, is that now let's prove that let's compute the genus of the rational function field. Yes. Yeah. Like max difference or just the difference? Right. So there I can help you. Also here I can somewhat help you, but not relating it to like Riemann surfaces. There I will fail. So the idea is that you look at a Riemann Roch space, L of A, and the degree, right, is you know how many positive minus how many negatives do you have, taking into account also the degree of the primes, but let's ignore that. And we said that positive means you're allowing poles, and negatives means you require zeros. So essentially, you know, larger degree means you allow more. And the dimension is the actual dimension of the Riemann Roch space. So you allowed, for example, in the rational function field, we looked at these things. These were degree R polynomials. And so you allowed for R poles, and you got R plus 1 degrees of freedom. But usually what will happen is that you will allow stuff, and you will increase it from R maybe to R plus 1. You'll say, let's say I'm increasing it by 1 more, just as a thought experiment. You're not going to do that. But, do I gain something? So you can show you can only gain 1 more degree of freedom, but sometimes you won't get any new degree of freedom. Namely, the dimension will stay the same even though you increase the degree, which kind of start to show that there is a gap, there may be a gap. And the reason there is a gap is you may, like, superficially, it seems like you allowed for more freedom here, but that freedom is not really a freedom because the algebraic constraints that you have doesn't allow you to use the freedom. Right, like the curve, the function field, right. In the rational function field, yeah. Right. The genus is going to be 0 as you'll see, and it's at least 0, so you know exactly what's the degree given the dimension. But generally speaking, there are relations, and the reason why, as you increase it, the deficiency goes up and up, is because you look, in a sense, more globally, or I don't know exactly how to say, you look at more and more algebraic relations. That, I mean, initially you are in your place, you are this function, and you increase, you at some point you gain, you may not gain new degrees of freedom because you sense that there is some algebraic relation. And as you increase it more, you sense that algebraic relation and that algebraic relation. And because, in a sense, because they're only like finitely many algebraic relation, it makes sense that the bound is indeed a bound. You can't like go to infinity. Once you got all the algebraic relation which are captured by the genus, you're done. I mean, right. So I hope it's helpful. And when we'll see examples, I think it will be more apparent. But yeah, we still don't. I think next time we'll see some examples. But okay, hopefully that was better. And the claim here is that the genus of the rational function field is 0. So what Yuval said was in the complex case, but actually, and you thought of as k being the complex value, then x. So you thought of the rational function over complex field, but it actually holds for every field. So this thing is 0. It's almost the only function field. Almost. We'll talk about it in the recitations, but essentially, up for like weird stuff, function fields don't have genus 0. They have higher genuses. Genera, higher genera. I think it's called genera. Like a plural of genus. You don't say genuses. Okay. I mean, you do if you don't know it, and when you understand that you should have said it. Anyhow, by the above remark, so how would you compute the genus? I mean, it's difficult to compute the genus by this definition because you have to go over all divisors, and who knows how a divisor looks like. But by this definition, I mean, it's not the definition, but it was we know that the maximum is that if you take an x, any x that you want, you don't have to consider any divisor. It's enough to take any x that you want, and you will take x to be x, and look at this difference as m goes to infinity. Because that's the same thing. That's how we bounded the genus. And then using this corollary, we said that actually it's the same number you get for every x if if m goes to infinity. So anyhow, g minus 1 is the maximum not over all divisors, but over all divisors like that. Right, so just to be clear, as m goes to infinity. And so let's see. Now x is very x is x. So what is the divisor, the principal divisor of x? Right. So so you have a 0 here. Sorry, you have a 0 here, and there is a pole, right? Right, exactly. And so we know what mx is. Mx. So we know that the degree. Let me write it. We need only the infinity, right? So m infinity is just this p infinity. So this degree is m, because it's m times 1. And the dimension, actually, that was the example that was here a second ago. What's the dimension of this space? Like, what is this space? At most m, right? So m plus 1. You said the answer. Oh, so m plus 1. Yeah, good. Right. Right, because these are all polynomials of degree at most m, including m, because this is just p infinity. This thing. Good. So this thing is always like 1. So this thing, even though it looks like it depends on m, is just m minus m plus 1, which is minus 1, and so g is 0. Yay. Questions? It's like a important part of the, it's like the fourth milestone that we did. So questions are in order. Oh, that's a great question. So we would prefer to have, we don't care about the genus per se in our coding, we'll see it now. We want the genus to be small compared to the number of points on the curve. We'll see. Reed-Muller is like a surface, so it's not a curve, but Reed-Solomon has genus 0. Reed-Muller is, actually, we don't capture it in this course.